Even when the content of your browsing is encrypted via HTTPS, the connection itself remains visible. The data inside might be secure, but the metadata, the digital breadcrumbs that explain who is talking to whom, is left entirely exposed to the infrastructure carrying it. This diagram illustrates the vantage point of an internet service provider. Because your traffic flows directly through their hardware, the ISP sees both your IP address and the destination server's address. This visibility links your identity to your destination, creating a permanent log of your behavior. Most users attempt to solve this by using a virtual private network. A VPN creates an encrypted tunnel that successfully blinds the ISP to your final destination, but it doesn't eliminate the middleman. It simply shifts the visibility to the VPN provider, which now holds that exact same metadata tag. This model replaces technical security with corporate trust. You are assuming the provider is not logging your traffic, that their servers are secure, and that they won't be compelled by a court order to reveal the link between your IP and the sites you visit. This structure ensures the connection between your identity and your destination is never actually broken. It is simply outsourced. As long as a single entity possesses both pieces of the puzzle, your privacy is a policy choice rather than a mathematical guarantee. The Onion Routing Protocol, or Tor, was designed to address this by ensuring that no single entity ever knows the full story. Instead of a single tunnel, it distributes trust across a decentralized web of volunteer relays. Before any data is sent, your Tor client queries a directory node to download a list of active relays. It then randomly selects a three-step path through the network: an entry node, a middle relay, and an exit node. Your computer negotiates a set of unique, ephemeral shared secrets with each of these three relays. These parameters are established locally, so keys are never shared between nodes. Your computer then performs 3 successive rounds of encryption on your data, creating a nested architecture, where each layer is specifically formatted for only one relay in your path. This preemptive wrapping rebalances the power dynamic. As the packet leaves your machine, the data is unreadable to the network, its destination buried beneath layers of decentralized mathematics. When the packet arrives at the entry relay, the node can see your original IP address, but it only possesses the instructions to remove the outermost layer of encryption. It has no way of seeing the final destination or the data hidden in the remaining 2 layers. As the packet moves to the middle relay, the second layer is removed. This node knows only which relay sent the packet and which receives it next. Unable to see the origin or destination, it acts as a blind spot, severing the link. Finally, the packet reaches the exit relay, removing the last layer and delivering the data. This node knows the destination, but has no knowledge of who originally sent the request. This multi-relay architecture means that capturing any single point in the circuit reveals nothing useful. The adversary sees either the sender or the destination, but never the correlation between the two. This sequential process successfully isolates your identity from your destination, solving the middleman problem for anyone navigating the open internet. While standard Tor usage hides the user, a vulnerability remains. The destination website is still located on the open internet, meaning its IP address and physical location can still be identified and targeted. To solve this, Tor supports .onion hidden services. This is an internal ecosystem where traffic never leaves the network, allowing a website to remain as anonymous as the users visiting it. To connect to an Onion site, your computer builds a standard 3-relay circuit terminating at a rendezvous point deep inside Tor. Simultaneously, the hidden server builds a circuit backward to meet it. This central point ensures neither side reveals their location. The rendezvous point bridges the 2 circuits, passing data back and forth without ever learning the sender's identity or the server's location. This 6-hop interaction creates a location-blind connection. Since neither the origin nor the destination is ever tied to a physical IP address, the network effectively eliminates the geographic markers that traditional surveillance relies on. The elegance of Tor lies in its simplicity. By replacing central points of failure with a distributed web of volunteer relays and nested encryption, it permanently separates identity from destination, ensuring that privacy is no longer dependent on trust, but on the architecture of the network itself.